Hi, this is Tzvi Rosen. Today we'll be talking about the Cohen-Seidenberg theorems, which are theorems relating the prime ideals in two rings in an integral extension. And this is a paper that this is based on. It's written by Cohen and Seidenberg, Erwin Cohen and Abraham Seidenberg. They were two students of Oskar Zariski, who was famous for the Zariski topology and many important theorems of algebraic geometry. They were not the first people to prove these results, but they did generalize them, as well as giving proofs that remained more popular. So the first person to prove these results was Wolfgang Krull, famous for the Krull dimension. Yeah, that's I think it's Stigler's law of eponymy that whoever something is named after is never really the first person to do it. So this is a shining example of that law. Okay, and here's a brief outline. We're going to see the lying over theorem, followed by the going up theorem and the going down theorem. In the big picture, we have an extension of rings, an integral extension. So we have A down here, and B up here, the larger ring, which is an integral extension of A. This is integral extension. And we want to know, how are the prime ideals of A and B related? So one theorem that is proved is the lying over theorem. And that's saying that if we have some prime ideal down here, we're also going to have a prime ideal up here such that the intersection of Q with A is equal to P. Okay, and that's called the lying over theorem, in essence because Q lies over P in this extension. We also have the going up theorem, and that describes chains of prime ideals. So let's say we have a chain of prime ideals, so P1 contained in P2. Then above, we have some prime ideal Q1 corresponding to P1, right? With the intersection of Q1 with A is going to be P1. Then we assert that we can find the prime ideal Q2, which contains Q1 and which corresponds to P2, in the sense that intersecting with A gives you P2. So this is the going up theorem, because it allows you to complete an upward chain where you have an upward chain in the lower ring, and in the upper ring you have the lower ideal, and we want to find a larger ideal that includes it, corresponding to the chain downstairs. So that's the going up theorem. As for the going down theorem, so the going up theorem says that Q2 exists, and the going down theorem says that in fact Q1 exists. So if we have a Q2 corresponding to P2, then we can find a Q1 corresponding to P1, but this is only satisfied in much more stringent conditions. In particular, A needs to be integrally closed, given we're already assuming that both of these rings are integral domains, but the going up theorem is true even where they are not integral domains, and the going down theorem is only true where the lower ring is an integral domain and the upper ring has some special condition on its zero divisors. So it basically, you can think of the going down theorem as being much more special than the going up theorem. Q1 exists. Okay, in terms of the tools that we're going to be using to do this, so we want to think about quotients. So whenever we can quotient out by an ideal, it basically says anything that doesn't contain this ideal is going away, and this ideal is now our zero ideal. So it allows us to kind of focus our attention at everything containing a specific ideal. Okay? And the other tool that we'll use a great deal is localization. And localization allows us to say only the things contained in this prime ideal are important. Anything that's not contained in this prime ideal is now just going to be the whole ring. So when you localize a ring, any prime ideal or any ideal that's not contained in the prime that you're localizing at is going to turn into the unit ring, the unit ideal. Okay, so that's the big picture of what we're going to be doing today, but now let's get to the details. First off, we're going to prove a lemma about integral extensions and fields. Suppose A and B is an integral extension of integral domains. Then B is a field if and only if A is a field. Okay. So let's prove this theorem. Start by supposing A is a field. Okay. Well, if B is integral over A, then for any x in B, we have some monic polynomial, which is equal to x to the n plus a1 x to the n minus 1 up to an equals 0. And now, moving the an over to the other side, and because A is a field, we can multiply an by its inverse. We have an inverse, and we can also factor out an x. Let's actually make this a minus an inverse, because we're going to move an to the other side. We can also factor out an x to get x to the n minus 1 plus up to a sub n minus 1 equals 1, right? Because we move the an to the other side. And we should note that an can't be equal to 0, but this is trivial to show, given that B is an integral domain. So if you had a polynomial whose constant term was 0, then you would have x times some polynomial is 0. So either x is 0, in which case it's in the field anyways, or the polynomial is 0, in which case we have a smaller minimal polynomial. Okay. So then, given this, so then we can just take this to be our inverse. Okay, so that means that, and clearly this is in B, because it's just a polynomial expression in x and elements of A. Okay, so that proves it in one direction, so so B is a field if A is a field. Okay. To prove in the other direction, suppose B is a field. Okay, so we need to prove that any element of A is invertible in A. So take A in A. So by virtue of B being a field, A inverse is in B. That means it has a monic polynomial. So exists P of x equals a to the n plus, oh, you know what, let's use a different letter. Let's call it y. Y in A, y inverse in B, and we'll make this P of y. So we have P of y inverse. So y inverse to the n plus up to an equals 0. By the same reasoning as above, an is not going to be equal to 0. So we multiply everything through by y to the n minus 1, right? So we're left with a single y inverse here, and then the rest of the expression is just expressions in y and the coefficients. But then that means that y inverse can be written as a polynomial in terms of elements of the field, of elements of A, which means that y inverse is in A. Okay, and that tells me that A is also a field. Let me just signify. So this expression is minus y inverse. Okay. Now we can discuss integral extensions and maximal ideals. This is another lemma going towards our Layover theorem. So let A be contained in B, be an integral extension, and Q in B is a prime ideal with P equal to the intersection of Q with A. Also a prime ideal, obviously. Then Q is maximal if and only if P is maximal. So let's prove this. It's actually pretty straightforward. If you take the quotient of B by Q, because Q intersect A is equal to P, this is now an integral extension of A mod P. Now this is a integral extension of quotients by prime ideals, so they're necessarily integral domains. And that means that if one is based on the previous result, the bigger field is the bigger ring is a field if and only if the smaller ring is a field. So by previous result, B mod Q is a field if and only if A mod P is a field. Okay. And if B mod Q is a field, that means that Q is a maximal ideal, and the same is true for P. That's just by the correspondence theorem. So this is equivalent to saying that Q is maximal if and only if P is maximal. Okay. Now we have a result called incomparability, which is often brought along with the Layover theorem, that if we have A and B an integral extension, and we have Q and Q prime, prime ideals of B, such that Q is contained in Q prime, and their intersection with A is P, then Q is equal to Q prime. Okay, so quick picture here. You have A and you have P. Up here you have B and Q prime. If they were both to intersect with P, to intersect A at P, then that must mean that they're just the same ideal to start. Okay. So how can we prove this result? Well, we use our main tools, right? Our tools are quotients and localization, so let's localize. Our multiplicative set, here, let's prove. The multiplicative set will be A minus P. Okay, so we're basically localizing A at P, and we're using the same multiplicative set for the upper ring as well. So localize with A, now let's call it S. S equals A, leaving out P. Okay, and in the previous lecture we proved that localizing in this way preserves integral extensions. So that means that S inverse B is integral extension of, it's integral over S inverse A, which is just AP. And we know AP is a local ring with maximal ideal P. Okay, so the image of this ideal, PAP, is maximal. Furthermore, when we localize S inverse B, Q and Q prime, because they intersect A in P, they don't meet this multiplicative set. So they're going to be preserved by the localization. So Q and Q prime are preserved by localization. Localization. Okay, and in terms of what their image is, well, we're going to have S inverse Q prime, because they meet this lower ring in a maximal ideal, they both have to be maximal. But you can't have a containment of maximal ideals, so that implies S inverse Q is equal to S inverse Q prime. But because the multiplicative set didn't meet these ideals, that means that the original ideals are also the same. Okay, so that tells us that these two ideals are the same, which is the notion of incomparability. If you have two distinct prime ideals that sit over the same ideal in an integral extension, they can't be compared. One can't be contained in the other. And now we get to the Layover theorem. Let A contained in B be an integral extension, and let P be a prime ideal of A. Then there exists a Q in B prime such that Q intersect A is equal to P. Okay? So we have a prime ideal lying over the prime ideal that we're interested in. So how can we prove this? Well, we're going to do the same trick of localizing at the complement of P and A. So proof, localize with S equals A leaving out P. Okay. Then S inverse B has a maximal ideal. Okay. By virtue of the theorem we proved earlier, whenever you have a maximal ideal in the upper ring, it's going to intersect in a maximal ideal in the lower ring. So let's call this maximal ideal M. So M must intersect A, or the lower ring, which is AP, really the localization, at the maximal ideal. There's only one maximal ideal, which is PAP. So in particular, when we look at the preimage of M before localizing, so the contraction of M by the localization, this must intersect A in P. Okay. Not only does it have the right intersection, it's also prime because it's the preimage of a prime ideal under a homomorphism. So we can take Q to be this contraction. Okay, and that's the Layover theorem. So again, just the broad structure of the proof. You localize at the prime ideal in the lower ring, and then take a maximal ideal in the upper ring after localizing, and then take its preimage before localizing. And that's the prime ideal we want. Okay, so what does this mean for us? So we'll want to think about the two primary examples of integral extensions and applications that we had, right? There were the first was number theory. We were looking at rings of integers. And the second was geometry. We were looking at, for example, maps from curves to lines. So in number theory, what this means is that if we're thinking about an extension of the integers, so if we have z down here, and let's say z adjoin 1 plus square root of 5 over 2 up here, then for any prime ideal here, there's going to be some prime ideal up here which intersects in precisely that prime ideal. Okay? There might be multiple such prime ideals, you know? You could have two different prime ideals corresponding to a given prime down here, but you know that it's not going to be an empty set. Okay, so that's what lying over means for us in number theory. In terms of the maps from curves to lines, basically means that if I'm mapping a curve to a line and it's an integral extension, for any point, I can find a point that maps to it. So that's surjectivity in a certain manner of speaking. And that brings us to the going up theorem. If you let A in B be an integral extension, and let P1 through Pn be a chain of prime ideals of A, and let Q1 through Qm be a chain of prime ideals of B with m less than n, so we have a shorter chain in B, then and Qi intersect A equals Pi for all I less than or equal to m, then Q1 through Qm can be extended to a chain Q1 through Qn with Qi intersect A equals Pi for all I less than or equal to n. So the picture of what's happening here is we have our extension A over B, or B over A, I should say. And then we have a larger chain here. So let's say we have, 3 ideals here. And then we have 2 of the corresponding ideals here. Then we should be able to find another prime ideal whose intersection with A is, let me give that a different color to say this is what we want to prove exists. It's this picture, that this red ideal exists. Okay, and it contains the other ideals, and its intersection with A is equal to the other ideal that we want. Okay, that's the going up theorem, because we have a partial chain and we want it to continue getting bigger, going up. So proving it is relatively straightforward. So you can first reduce to the case where n equals 2 and m equals 1. Because if you have any longer chain, just cut it down to the first missing element, right? So we're looking at P1 contained in P2, and then we have Q1, and we want to find the corresponding Q2. So what we can do straight away is quotient out by P1. So take B mod Q1. This is an integral extension of integral extension of A mod P1. Okay. And then by the lying over theorem, there is a prime ideal in this quotient ring. So first of all, by the correspondence theorem, we have a prime ideal in the quotient ring corresponding to P2. Okay, so the image of P2 in this quotient is prime. And so by lying over, we have there exists, let's call it Q2 tilde in B mod Q1 with Q2 tilde intersected with A mod P1 equal to P2 A mod P1. And given that Q2 tilde, and this is obviously prime by the lying over theorem, and so taking that Q2 tilde, the correspondence theorem gives us another prime ideal in the original ring B containing Q1. So the correspondence theorem says that this Q2 tilde corresponds to prime ideal Q2 containing Q1, whose intersection with A is P2. Okay, and that's exactly what we need. So it's as straightforward as just quotienting out by the bottom ideal and applying the lying over theorem. So what does going up give us? Well, in number fields, we really just have we don't really pick up much more than the lying over theorem, because the number fields generally have curl dimension 1, so you're not going to have very long chains. But one of the concepts that we'll define later is curl dimension. This is an alternative definition of dimension in the geometric sense, and this is the length of a longest chain of prime ideals in a ring of, let's say, distinct prime ideals. Okay. With this definition of dimension, the going up theorem implies that, so going up implies that for A and B in an integral extension, the curl dimension of A must be equal to the curl dimension of B. The reason being that if I can construct a chain of distinct prime ideals down here, P0, P1, up to Pn, then I need to be able to construct a similar chain of prime ideals up here, Q0 up to Qn. So you might say, well, with the going up theorem, I have that the upper chain must be at least as long, but how do I know that it actually is as long? Well, at least long, but maybe it could be longer, you might say. Well, if we were to have a longer chain here. So let's say we had Qn and then Qn plus 1. So well, then that would contradict what we know about the fact that a maximal ideal, if you have a prime ideal in the top ring intersecting the bottom ring in another prime ideal, then one is maximal if and only if the other one is maximal. So we can, by the fact that Pn is maximal, since this is a maximal chain, that tells us that Qn must be maximal. So that tells us that this is not going to be in that chain. Okay, cool. So, so that's a consequence of going up, and in the context of geometry, this tells us that these rings, which are associated to certain varieties, if they have this property of integral extension, will be of the same dimension. So the dimension of these geometric objects will be the same. Okay, now we'll move on to a discussion of going down, which requires a bit more work. Again, that means that we have the bigger prime ideal, and we want to prove that the smaller prime ideal intersects the base ring in the appropriate way. Okay, so we'll start by discussing integral closure in localizations. Take A and B, both rings, and see the integral closure of A in B. Let S be a multiplicatively closed subset of A. Then S inverse, the localization of at S of C, is the integral closure of S inverse A in S inverse B. Okay, so let's prove this. Okay, and this is a lemma that we'll need later for the going down theorem. So suppose we have x over s in S inverse A, in S inverse B, which satisfies a polynomial relation, a monic polynomial relation in S with coefficients in S inverse A. In other words, that it is integral over S inverse A. So what does that mean for us? Then we have so P of t, where this is t to the n plus a1 over s1 t to the n minus 1 plus an over sn equals 0 has p of x over s equals 0. Okay. Well, plugging that in, we get x to the n over s to the n plus a1x to the n minus 1 over s1 s to the n minus 1 up to an over sn equals 0. Okay, so we're going to take t to be equal to the product of all of the si's. And then we're going to multiply both sides of this equation by s times t raised to the nth power, or s to the n times t to the n. So then what we get is t to the n times x to the n, because the s to the n cancels, plus, well, one of the s1s cancels here. So we have t to the n minus 1, and then we have everything except s1 here, so s2 through sn. And then we also have a factor of s. The rest of the s to the n cancels with s to the n minus 1 times a1 x to the n minus 1 plus all the way through to again, we get, so it's t to the n minus 1, and then everything besides Sn, so Sn minus 1. And we also get an and s to the n. Okay? So that will be set equal to 0. And what we see in this equation is now all of the coefficients are elements of A, right? The AIs are in A, the S's are in A, the SIs are in A, and the T's are in A. So what that means for us is that this is a new polynomial, p tilde of tx, which is equal to 0, with coefficients in A. So that means that tx is integral over A, okay, which means in turn that means tx is in C, which means also that we want x over s to be in S inverse of C, but it is because we have tx is, you can divide this by st, since st is in S. So tx over st is equal to x over s, and we can now confirm that this is in S inverse C. Okay, so everything which is integral over S inverse A is in S inverse C, and clearly everything in S inverse C is integral over S inverse A, so we have the result. Okay, and now using that we can prove that being integrally closed, i.e. being equal to your integral closure, is a local property. And this is going back to our section on localization and local properties. The ring A is integrally closed if and only if the ring A localized at P is integrally closed for all P prime, if and only if the ring A localized at M is integrally closed for all maximal ideals M. And the key here is to take the map sending f from A to the integral closure of A and here we're just taking this map to be the identity. Okay, so clearly every element of A is in the integral closure. So you can just map it to itself. And now the question is this map F surjective? Okay, so if there's nothing besides A in the integral closure, then that's going to be surjective, which means that A is its own integral closure. So an A-module homomorphism being surjective is a local property, and that's something that we proved in the local properties section. So f from A to, let's call this C, surjective if and only if f localized at P from AP to CP is surjective, if and only if FM sending AM to CM is surjective. And the key here is to see that these rings are localizations of the integral closure, which means that they are also the integral closure of the localization, based on the previous results we proved. And so that's what tells us that we're proving the same property for each of these localizations. Okay, and this is a property. So surjectivity is a local property, and then see the section on localization. Okay. Now I'll just make the note here that localization of integral closure equals integral closure of localization. Okay. Okay, apologize for the mess. Okay, now let's make a brief definition. What does it mean to be integral over an ideal? Well, if A is in B and x in B satisfies a monic polynomial x to the n plus a1 x to the n minus 1 up to an equals 0, and then all of the ai's are in the ideal A, then we say that x is integral over the ideal. Okay, it's a more restrictive condition than just being integral over the ring. Okay, now we'll prove the following lemma. Again, all of this is working towards the going down theorem. Let's consider the integral closure of an ideal. So we say that if C is equal to the integral closure of A and B, and A in A is an ideal, where AE is the extension of A to C, then the integral closure of A in B is R of AE, the radical of the extension of A to C. And what we mean by integral closure here is the set of all elements integral over A in the sense of the previous slide. Okay, so let's prove this. So if we have an element in B which is integral over the ideal A, then by definition we have a polynomial x to the n plus a1 x to the n minus 1 up to an equals 0. So the ai's are in A, but they are also in the ring A, which means x is integral over A. So this means x is integral over the ring A, which means x is in C. Okay? The next thing to notice is that if we keep x to the n on one side and move everything else over, what we find is that we have this polynomial expression for x to the n in terms of the ai's and x and powers of x, lower powers of x. And this tells us that x to the n is in the extension of A to the ring C, right? Because we're multiplying elements of the ideal by x, which is an element of C. But that means that x itself is in the radical of the extension. Okay? So that shows containment in one direction. Certainly the integral closure of A and B is contained in the radical of this ideal. As for going the other direction, so that proves this way. Going the other way, well, we know that if x is in the radical of AE, that means that there exists an n such that x to the n is in A, E, and that means that x to the n can be written as some A linear combination of elements of C, or rather a C linear combination of elements of A, whichever perspective you want to take. Yeah, C linear combination of elements of A is the correct one. So we have x to the n is equal to the sum of the ai xi, I equals 1 to m. But that means that x to the n is contained in A adjoin x1 through xm. And since they're all integral, this is a finitely generated module. But that means you can apply the Cayley-Hamilton theorem, the version which includes the ideal. So the Cayley-Hamilton theorem implies the result. Okay. Still gathering these lemmas to prove going down. So for proposition 5.15, we have A contained in B, and they're both integral domains. A is integrally closed, and we have some x in B integral over an ideal A in A. Then x is algebraic over K, the fraction field of A, with minimal polynomial over K given by t to the n plus a1 t to the n minus 1 up to an. Okay, so given all of these hypotheses, then these a1 through an lie in the radical of A. Let's prove this result. So if x is algebraic over K, then its minimal polynomial has all of its roots contained in some algebraic extension. So if we have L over K, then we're saying this has x1 through xn, all roots of this polynomial p of t. Okay. Well then, in terms of what the coefficients of p of t are, they're all going to be elementary symmetric functions in the xi's. Okay, so the polynomial then, p of t, is equal to t to the n plus some symmetric, some sigma 1 of x1 through xn, etc., times t to the n minus 1, plus up to sigma n of x1 through xn. These are the elementary symmetric functions that appear in polynomials. Okay, so all of these xi's are solutions to this monic polynomial. So that means that they're all integral over A. Okay, so the xi's are integral. Now let's go to a new slide. All of the xi's satisfy the same polynomial as your x, satisfy the same monic polynomial as x, so that means that they're all integral over the ideal. Okay, well, once we have all of these elements being integral over the ideal, then the polynomials in those elements are also integral over the ideal by any of our equivalent conditions for elements being integral. So that means that the elementary symmetric functions in the xi's are also integral over a. But we know that the closure of the integral closure of an ideal is going to be given by the radical of that ideal. So that implies that all of the coefficients of this polynomial are integral over a, which means that they're in the radical of a. Okay. And that proves the result. That's what we were looking for. Okay. And finally, we arrive at the going down theorem. So we have A and B, an integral extension of integral domains with A integrally closed. Then if we have a descending chain, so P1 contains P2 down to Pn, and Q1 contains, and those are prime ideals of A, Q1 contains down to Qm of primes in B, where m is less than n, and such that Qi intersect A is Pi for all of the i's at most m, then the chain can be extended. So again, our cartoon, we have our B, we have our A, and if we take a descending chain here, if we have an ideal that matches the top one here, then we need to be able to find an ideal inside of it that matches this smaller one. Okay, that's the going down theorem. Okay, and as we can see, we have a lot of requirements for it. So let's try and prove it. Okay, so let's consider the first thing that we'll do is reduce to n equals 2, m equals 1, right? You don't need the whole chain, you just need to know that if you have 2 and 1, you can step down, because that's enough to extend any chain. Okay, and the way that, and then once we have P1 contains P2, and Q1 intersect A equals P1, what we're going to do is localize B at Q1. Okay, so take B localized at Q1. That means everything outside Q1 is invertible, and now Q1 is our unique maximal ideal. Okay? So we're localizing there. So we're going to hope that our Q2 will just be equal to the ideal generated by P2 when you extend to BQ1. In particular, we need to show that P2 BQ1 is, when you intersect it with the ring A, all you get back is going to be P2. Okay? So if we can prove that, then we'll have the desired prime ideal that, that we're looking for. So let's take an element of P2 BQ1. So we have y over s, where y is in P2b and s is in b minus q1. Okay, we saw that the extension of an ideal is equal to the integral closure, or rather the radical of an extension of an ideal is equal to the integral closure of the ideal. So that means in particular for y, that y is integral over the ideal P2. Okay. So what that means for y is that y to the r plus, let's make it a1 y to the r minus 1 up to a r equals 0, where ai is in P2. Okay. So we're trying again to prove that this is this has intersection with a equal to P2. So suppose we have x in P2 BQ1 intersect A. Okay, so by what we just wrote, we have y over s equals x, which means that y is equal to x s inverse. Okay. But this also means that, by xs, this also means that s is equal to y over x. Okay, well, looking at this last equation, if I divide through by x to the r, what I get is y over x to the r plus a1 over x times y over x to the r minus 1, etc., all the way down to ar over x to the r equals 0. So this tells us that s also satisfies a certain monic polynomial. Okay. Now let's look at the coefficients of that polynomial. They all are in P2 times some inverse of an element here. So using the result that we had regarding minimal polynomials and how their coefficients are forced to be in a particular ideal, so the fact that s is in A means s is integral over A, and in the language of ideals, it's integral over the unit ideal. So that means that this minimal polynomial that it satisfies, this monic polynomial, has to have all of its coefficients be in this ideal. So this means that ai over x to the I is in A for all I. Okay. So we know that ai is in P, is in P2. If x is not in P2, okay, and we're hoping to show that x is in P2, but if x were not in P2, which is, we'll assume for the sake of contradiction, then ai over x to the I times x to the I equals ai, so we know that has to be in P2. So that means that this must be in P2 by primeness. Is in P2 for all I. Okay. But then that means that S is integral over P2. And this means that S to the R is in BP2, which means that in particular, it's contained in BP1, which is the larger prime ideal. And we know that's contained in our maximal ideal up top. So this tells us that that S itself, because Q1 is a prime ideal, S itself must be in Q1. But we started out assuming that S was not in Q1. So we've just arrived at a contradiction. Based on that contradiction, we conclude that the opposite of this is true. So indeed, X must be in P2. Okay, and that gives us the going down theorem, that this intersection of, or rather this intersection of P2 BQ1 with A is in fact the prime ideal we're looking for, and so that prime ideal up top is valid. Okay. Key part of this proof throughout was the notion of being integral over an ideal. Right? We needed that concept in order to find the monic polynomial with coefficients all in our smaller ideal P2, so that we could confirm that the larger ideal has the smaller ideal in the extension of the ring B has the right intersection with the smaller ring. So that's why we introduced this concept of integral over an ideal. Okay, so final slide here is just to demonstrate that this concept of being integrally closed is really essential to the theorem, the going down theorem. Okay, obviously we didn't need it for the going up theorem, but it is necessary for the going down theorem. And this example is provided in the original paper of Cohen-Seidenberg. And they make a note that Professor Zariski advised them on this example. And the pictures that we're looking at here, this is, we're looking at two algebraic varieties. So the first is K adjoin X, Y, Z, modded out by the polynomial y squared minus x squared minus x cubed. Okay, so that's the coordinate ring for this variety. Okay, and you can tell this polynomial in x and y defines this elliptic curve you see over here. Okay. The coordinate ring of the variety on the right is what you get when you take the integral closure of the one on the left. So if you take k adjoin x, and then there's this integral element y over x, which isn't in the left-hand coordinate ring, but is in the right. And when you quotient out by, and instead of quotienting out by the original polynomial, now we can divide it by x squared and get this polynomial, y over x squared minus 1 minus x, which is why this looks a little bit more like a parabola. So the reason that you don't have this going down, the going down theorem for these rings, because, so first of all, you know it's not integrally closed. The lower ring is not integrally closed. So the illustration of this is that we have these two blue points on the right, which correspond to this single blue point on the left. Okay, so these are two maximal ideals that correspond to one maximal ideal here. And then there's a curve that passes through the maximal ideal on the left, but on the right, it only passes through one of those maximal ideals. And there's no similar curve which restricts to the one on the left that would pass through the other one, right? So this, something like this does not exist. No candidate curve. Okay, so even though you have, so if I mark this as my P1 and this curve as my P2, if I were to take this as my Q1, its intersection with the coordinate ring down here is in fact P1, but there's no valid Q2, which would restrict to P2. And the proof of that is left to you as an exercise, and I thank you for your attention.